Ahora sí. Okay. Hi, everyone, and welcome to this edition of the CAB seminar series. As usual, this talk's going to be recorded and uploaded to YouTube. So hi to everyone who's watching this back on YouTube as well. Now, it's my absolute pleasure today to welcome Itziar Aretxaga, who is a distinguished researcher here at the CAB since 2025, having moved from Mexico only just recently. And Itziar is an expert in dusty starburst galaxies. Now, she started her career here in Madrid as well, completing her PhD at the Universidad Autónoma de Madrid in 93. And she then obtained a Marie Curie fellowship and took that to the Royal Greenwich Observatory in the UK and also to the Max Planck Institute for Astrophysics, the MPA, in Germany. She then moved continents to Mexico, where she took up a research position at the Instituto Nacional de Astrofísica Electrónica y Óptica, where she became a full professor in her 27 years at that institute, and then subsequently the head of astrophysics. And like I say, in 2025, she moved here to the CAB as a distinguished researcher. And among her many roles, she's the project scientist of the TolTEC instrument on the Large Millimeter Telescope in Mexico. And she's also the director of the IAU's International School for Young Astronomers. So with that, I'll hand over to you, Itziar, and say thank you very much for agreeing to give this seminar, and I'm really looking forward to it. Okay, you've got a microphone there, so I think you're all sorted.
Okay. Well, it's my absolute pleasure to be here. I was in the queue to give a seminar, and I seen so many people from CAB who were going to speak. I thought, oh, it will be next year. And then suddenly they contacted me early this year and said, could you give this slot? And I said, absolutely. So thank you. Thank you to the seminar organizers for giving me a slot. And thank you to all of you for making time in your schedules to come and see what this project that I am going to be leading here at CAB is about. So I was granted this tri-action by the Spanish ministry to attract consolidated researchers from all over the world. I am actually bringing a project that I was already leading in Mexico to establish a group here that will do this contribution to understanding what dusty galaxies contribute to the star formation history of the universe. Patrick already mentioned it. I am on leave legally right now. Hopefully soon this will be my old institute and be hired here more permanently. But this is the group of people I have been working with over the past years, and to which I have to acknowledge the work that they have done for the contribution in this talk. So there are 5 PhD students, one of them already graduated, and Alfredo Montaña, my colleague at INAOE, graduate students, you will see their work, my colleagues Aldo Rodríguez Puebla and Vladimir Riz at Universidad Nacional Autónoma de México, who will come towards the end of my talk in their contributions. For those that do not know INAOE, this is what the institute looks like, and these are the instruments that we had access to. My talk is going to be based mostly on this facility, which is the 50-meter large millimeter telescope, a telescope optimized to do observations between 1 and 3 millimeters. And the TolTEC camera is already mounted there, as I will show. But INAOE has access to the Hawk high energy telescope, to the GTC through an agreement with a contribution to the GTC, who is located in Spain, has small observatories, a historical telescope that was key in order to put the seeds on how stars form with the Herbie Arrow type of objects. And the LMT actually has access by the Spanish community through an agreement with the GTC. So GTM time is open to Spanish proposals. So because I was told to just give a general introduction for everybody in CAP with different backgrounds, I would like to just start with a very general topic that actually is at the heart of why we're doing surveys. And it is Olbers' paradox. Why is the sky dark? I mean, this is a paradox that plagued all the 17th, 18th, 19th century. And it was resolved through the discovery of the expansion of the universe, but it goes by that. I mean, why, when we look at the sky, is it dark? Why don't we see the integrated light from the zillions of stars that should be populating a homogeneous and isotropic universe if this universe is infinite and if it is static, right? This was the framework for cosmology before the Big Bang theory, basically. So we will expect that the night sky is infinitely bright, if that were the case, and clearly everybody knew that that was not the case. And I don't know whether this is as well known, but a poet that many of us admire, Edgar Allan Poe, actually in his work Eureka, came to the conclusion that the universe could not be static and infinite. And so it was the first person just using Newtonian mechanics that said the universe should be evolving. Of course, afterwards, with the use of general relativity, cosmologists discovered that the standard solution for the whole universe was an expanding universe, which is our current model. So our current model for the history of the universe is there was a start. We call this the Big Bang. Shortly after the Big Bang, the first particles were created. The first nuclei, the first chemical nuclei were created about 380,000 years after the Big Bang. The nuclei were combined with electrons, and that allowed for the cosmic microwave radiation that we can see. In that, we can see the seeds from which galaxies were to be formed. And now, actually, with fantastic telescopes like the JWST, we can reach back to very, very early times in the universe. With the Large Millimeter Telescope, if there is dust, we also can reach to these types of ages over here. And more recently, the content of dark energy in the universe is kicking in so that the expansion of the universe is accelerated, and we are studying all of that from here in a chemically enriched universe where galaxies are well formed and we can study them in great detail. But reconstructing how these galaxies came to be is one of the key aspects that we do in the astrophysics department of CAP and in other departments. So is the sky really dark? Well, no. I mean, we know that Olbers' paradox is actually a paradox that has been solved because of the expansion of the universe, but also the sky is not fully dark. And this we can see when we combine observations to parts of the sky that look blank, that don't have any big structures in our line of sight. And here is one of them at infrared wavelengths, the Hubble Ultra Deep Field. This is the counterpart at millimeter wavelengths with ALMA of exactly the same field. And we can integrate what light is in those dark patches of the sky, and it is not completely zero. There is emission at different wavelengths. Just taking out the CMB, which is represented here, what we have here is the energy radiated by the sky against wavelength. So taking out the CMB, which is certainly the most important contribution in photons in the universe, but just looking at other contributions from already astronomically formed objects in the sky, we see this contribution in the optical, which is highlighted here in blue, and we see this contribution in red. There are these two mountains of emission. which are approximately equal in energy output. So when we want to characterize what objects contribute to the evolution of the universe, we need this complementary view of what comes in the optical, what comes in the far infrared. And the surprise often is that both of them are difficult to relate to each other. So we need simultaneous observations, not in time, but at least in the same patches of the sky in order to reproduce the type of galaxies which are contributing to the energy emission in the universe. Why do we have those two mountains? This is tried to explain here the effect of dust. Dust are these heavy element aggregates that we can see in nearby objects mixed in the interstellar medium. This is just a dust grain just extracted from the interplanetary area through missions, but it is a good analog of what we think interstellar dust might be, maybe in a smaller particles than what we are seeing in this picture. But they are aggregates from a few molecules to around 0.1 millimeter that absorb optical and UV light and re-emit because they are heated into the far infrared. So that is portrayed here in this plot. I mean, you will expect from a single stellar population of stars which are born at the same time to have an energy output like that portrayed here in blue. That is millions of stars radiating together with different masses. But if you throw into the interstellar medium a little bit of dust, the UV and optical light from this blue curve gets suppressed to go into the black part of the curve. And this energy has to go somewhere, obviously. So it is emitted in the far infrared, which is represented here in green. So the total output of this particular nearby galaxy, NGC 337, which observationally is here represented by these red points from 0.1 to 1,000 microns, can be reproduced by this population analysis, just throwing in a little bit of dust. That actually gives us what is the dust mass, which is in this type of objects. Now we have come from a seminar on sub-millimeter galaxies, those that were in the extragalactic meeting. So these are galaxies which are dominated by dust emission. They have so much dust that the optical part of the mountain, which is over here, is suppressed by 2, 3, 4 orders of magnitude. And most of the emission is dominated by the dust emission. It's by these heated gas dust grains, which are just mixed with the gas in these galaxies. Typically, these galaxies are high redshift. We will see that in a minute. But also because they are high redshift, they solve, or we believe they solve, another old problem that galaxy evolution had. And it is, where are the big galaxies, the spheroids that we see, the big elliptical galaxies, when have they formed and where are they in formation? Because first rank elliptical galaxies nearby have very large masses, in excess of 10 to the 12 solar masses in stars. We know the stars are very old. They are stellar population analysis that place them at redshift 3. Redshift 3, if I am not mistaken, have I put it there? No, I haven't put, oh, it is there. It is roughly 2 gigayears after the Big Bang. And so you know that you have to form these stars, maybe not in the same place, but at least you know that all these stars have to have formed by redshift 3 or before. And they have had to assemble into an elliptical galaxy. So this is a back of the envelope type of calculation that I usually teach to my first year grad students in masters. And so you take a first rank elliptical mass, 3 times 10 to the 12. You have 2 gigayears available from the beginning of the universe to redshift 3 to actually form those stars. And you expect to have systems forming stars at around 1,500 solar masses per year. Now, these systems, now we know they exist, but for many, many years, when I was a PhD student back in the 90s, they were a problem because we could not see them anywhere. I mean, we actually have started to solve this problem by looking at the far infrared. They are not seen at optical UV wavelengths. You don't see this type of systems. They are heavily embedded in dust. There already has been some chemical enrichment in actually to just have these big factories of a star formation in the universe. And this is just one of the first images that was taken at submillimeter wavelengths, just showing this type of very, very effective star formation factories. The SED, I just mentioned, was very, very suppressed at optical wavelengths, very bright at millimeter wavelengths. And because we have so much emission at millimeter wavelengths, these are galaxies which are very easily found. And this has to do with wherever we are looking at millimeter wavelengths at these galaxies, as we play these galaxies at higher and higher redshifts, of course, we are making them dimmer because they are farther away. And of course, the flux is divided by dl square, the luminosity distance square. But because we are sampling the SED redshifted, we are sampling the SED at shorter and shorter wavelengths into the emission of dust. And the cosmological dimming actually compensates the climbing into the dust emission, and the net effect is that if you look at the same luminosity type of galaxy, you have a flat surface, a flat density, flux density detected at your telescopes. So a 10 to the 12 solar luminosity system, which is already forming stars at 100 solar masses per year, you will find it easily in your surveys if you can detect at least a fraction of a millijansky in your surveys. So you explore a huge volume with this type of surveys. It is a very powerful wavelength to look for this type of galaxies. So what are the properties of these galaxies? We know that they form stars very efficiently. Now we know a medium redshift distribution. Actually, there is a lot of debate about whether the tail is more extended. Most of these galaxies have actually very well star-formed systems. I mean, there is some debate about this as well, which IMF you imply, which models you use, but certainly they are formed, they are well formed of a few times 10 to the 10 solar masses at least. And here in this sample, a few times 10 to the 11 solar masses. Now, are all of them lensed galaxies, as we saw in the seminar? What type of galaxies are there? Actually, they are a mixed bag of galaxies. These are non-lensed galaxies, but very bright, 10 millijansky galaxies. Aztec 1 is one of these beasts, is a disk galaxy. It has been well studied with ALMA. These are the counterparts when we did we first found this system in the beginning of the 2007, I believe we published this paper. It took us 10 years to actually find the redshift for this galaxy, and then to have the follow-up of ALMA years afterwards. This is a galaxy, a redshift 4.3, so only 1.4 gigayears after the universe started, 1,200 solar masses per year. Huge beast. I mean, it is almost in the hyperlark type of regime, order disk, but fraction. I mean, it is actually being fragmented, is turbulent and forming stars. It's not interacting, it's not actually amplified as far as we know. Are all like this? No, they are interacting systems which are as bright as this one. They are lensing systems. It's a mixed bag. So up to now, with the different array of telescopes, we have actually, single disk telescopes, we have actually explored, I will say, well, this type of regime. This is where Aztec 1 is, the two systems that we saw earlier today also are very, very bright once you delens them. I mean, I don't know exactly where they are, but they will be in the ULERC to hyperLERC type of regime, 10 to the 12 to the 10 to the 13 solar luminosities, so systems which are forming stars in excess of 100 solar masses per year as the whole galaxy, some of them 1,000, 2,000, 3,000 solar masses per year. But already with single disk telescopes, we have been able to explore this type of regime, certainly with ALMA, but in very small samples. And they are not as spectacular as Aztec 1. These are just JWST counterparts of some of these 10 to the 12 solar luminosity type of systems. This is a paper done with HST type of data. And what we are seeing here is the specific star formation rate versus the stellar mass of the systems. Yeah, to try to understand whether they are exceptionally star forming or they are just star forming at a normal rate of what we call the main sequence of star formation, which is here marked in red. The black points are star forming galaxies, which are selected through UV infrared type of measurements, and the red points are submillimeter galaxies, which have been selected with submillimeter surveys. And it might be apparent to you that there is a tendency for the red points to be above that line. So it means that they are more star forming than normal, although there is a mixed bag. There are some of them which are suppressed. And also, when you look at their morphologies, their optical infrared morphologies, we know that at redshifts 2 to 3, they have 50% larger sizes. And actually, just looking at the morphological classification, we can see more interactions in that redshift regime. Can all this be done only with the JWST surveys? We see them, but can we infer their properties just from optical to near-infrared wavelengths or mid-infrared wavelengths? And this is a diagram, again, shown in the same paper. What we are plotting here is what happens if you have long wavelength, far infrared measurements coming from, I don't know, from 850 microns to 1 millimeter or beyond. And what happens if you just use the candles data, that often they don't have that information. And what you can see is that there is a lot of scatter in this type of information. So it's very difficult to extrapolate from optical, near-infrared, mid-infrared to far-infrared properties. I mean, we know that there has to be emission from cold dust in these galaxies, but how much is difficult to correct for. And quite surprisingly, at least to me, is those that have the highest discrepancies that have in the optical the smallest extinction values. And this is again indication that these are not homogeneous systems, they are clumpy. Some of the regions where you have star formation is very embedded. You don't see the optical emission from them, and you might be seeing optical emission from regions which are star forming but less optically embedded into the dust. So you do need this complementary view. And this complementary view maybe is reflected in this diagram the strongest, which is what cosmic star formation history can we infer from different surveys. And this is an old plot and an old analysis that has been done since the year 90s, right? And here it is condensed in this paper by Jorge Zavala with what is the star formation rate density, how much star formation rate per cubic gigaparsec or cubic megaparsec is measured in this type of images from optical near infrared without correcting for dust, and that is the blue curve. And in red, we have what inferences we can have from millimeter wavelength or Spitzer type mid-infrared long wavelengths into how much star formation is going on in the universe. And what you can see is, of course, if you correct by dust, you will hit very easily this curve here, because in the end, some galaxies are common to one another. But when you go to high redshifts, there is a huge uncertainty in what is the contribution from dust in star formation reconstruction, how much obscure star formation there is, and how much we can reconstruct it. This is just a more recent diagram, just highlighting exactly the same. Here's the total star formation. This is an obscure, so not corrected for dust emission. And these are just measurements done at redshift around 7 in tiny, tiny regions of the sky, highlighting that for selected galaxies at that redshift, there is a lot of dust. How much there is still a matter of debate, and there are constant papers, one group highlighting the heavy contributions of dust at redshift beyond 4, others highlighting that by redshift beyond redshift 4, you are dominated by non-obscure star formation. This is an open question. ALMA is trying to do its best, but ALMA is actually not putting much effort into blank field observation. So what it's doing is follow-up of selected sources, whether they are selected from JWST or they are selected from our single disk submillimeter surveys. But we still do not know what the common dusty star-forming region is contributing at high redshift. This is something that is waiting for new surveys to come to line. This was highlighted actually 2024. We had the Capley IAU think tank about where the field will be in the next 30 years. And it was recommended to the whole community that there had to be 2 lines of exploration. One of them is a far infrared space probe in the 20 to 200 microns. PRIMA, which is a project still not fully approved, is one of the main candidates for being the next space generation probe into the far infrared peak. Very important for galaxy formation and evolution, but also for any other common user type of project. And also a single disk submillimeter, 350 micron to 10 millimeter efficient telescope with large field of view that can actually scan the universe and just probe where dusty star-forming regions are happening. A fast survey tool. The LMT comes to answer this question with an efficient TolTEC camera, but there are other groups working on this. So Europe is actually leading a new telescope, the Atlas telescope, that maybe it will come in line in the next 10 years. And there are groups at CSIC which are heavily involved in this. I think that this is a very interesting avenue as well, because putting such a dish in Chile will access the shorter wavelength regime that the LMT cannot cover. But in the LMT, we were doing our best. So we formed this collaboration, TolTEC. TolTEC is a millimeter wavelength camera imaging simultaneously 1.1, 1.4, 2.1 millimeters. Why those 3 wavelengths? Because they are easily accessed from a high ground facility. We have windows there to just map these 3 regions, but also those are 3 regions which are key in order to look for Sunayet-Seldovich type of signal. I mean, you will see a decrement in the signal with respect to the cosmic microwave radiation due to the interaction of cosmic microwave background with the hot gas in clusters of galaxies. You will see a decrement, an increment, and a null in these 3 wavelengths. So it is actually designed in these 3 wavelengths to look for Sunayet-Seldovich effect, but actually dusty galaxies will be picked up in the 3 wavelengths. And so that is also important because it will give us views into what type of emissivity the dust in these galaxies have. Okay, the project is led by Grant Wilson in the University of Massachusetts. He is the PI, I am the project scientist, and we have 7 institutions which are partners to this telescope. The telescope is a collaboration between the University of Massachusetts in the US with NSF funding now as well, and Mexico through CONACYT funding. INAO is the representative for Mexico, and the Mexican team is heavily involved in all of the projects. So what we are planning to do? There are 4 legacy surveys that we have approved. Each of them will have 100 hours of observation with TolTEC. None of them have yet started, but we are doing the commissioning for the 4 of them, which have been approved. 2 of them are extragalactic, which are the ones that I am heavily involved in, the ultra-deep survey of star formation. So going as deep as the telescope can go in order to look for these galaxies over a 0.8 square degree area. And the large-scale structure survey actually will be shallower, covering 60 square degrees, and that's targeted to look for the large-scale structure, for how the galaxies, the dusty galaxies, are located within their environments, looking for clusters, looking for clustering, etc. And this is a diagram that basically places our surveys, our planned surveys, with respect to where is the field right now. What we have here is map depth at 1 millimeter with respect to map area. Of course, ALMA surveys are the deepest. The deepest ones are over here, like the ultra deep field is over here. It's a tiny area, but very deep, much deeper than the LMT can go. This is our limit for the telescope, what we call the confusion limit, where very faint galaxies are merged into the beam, and then we cannot actually isolate one from the other. And we believe we will be able to operate between these gray lines. This is our area of uncertainty depending on performance of the camera. Although we are doing commissioning, we still do not know where we are because there is readouts of detectors that we still have to reconnect in order to prove fully the mapping speed of the camera. These are in points, several surveys in green from ALMA, some blank fields from ALMA over here, here from NICA 2, in the IRAM telescope, from the JCMT with the Scuba 2 camera. And so we're hoping we can do an order of magnitude deeper than what has been done up to now. So that means that instead of being subscribed to the Euler regime and above, we will be able to go blankly, not targeting already known surveys, sources, but just looking for what there is above the luminous infrared galaxy type of limit. This is our goal. Okay? Well, I'm not going to go into the details of camera, but it's a new generation camera, much like NICA 2. I mean, technology which is kind of similar, is these kinetic inductance detectors, very fast in principle, very complex to do the readout. TolTEC was installed in 2021 at the telescope in the middle of the pandemic. The pandemic was devastating in Mexico because we didn't have good protocols for going back to work. So we could not actually operate in the telescope for the whole 2020, 2021. Only in 2022, we started taking commissioning data. So commissioning data has come, and we have actually advertised it. This is M1, the Crab Nebula, seen at 3 bands by TolTEC. I mean, you might not notice this, but this is a color map. We are actually seeing the differences in emissivity indices from different parts of the nebula. I say it's just a demonstration type of image. And TolTEC has polarimetric capabilities, so there are also the information of where the magnetic fields are oriented and how they are oriented, especially for bright sources. I mean, we might be able to do some extragalactic sources which are very bright, but in general, the galaxies will just have continuum observations. I like to show continuum observations of submillimeter galaxies because this is not yet public. This is still ongoing. And one of the PhD students in Mexico, Daniela Espitia, is working on this very bright source. This is Aztec C1 in the Cosmos field, not the one that I showed before. That's Aztec 1. This is Aztec C1. I know the nomenclature is a bit nuts. It's not too deep yet. It's like 0.2 millijanskis, but we are performing actually right now better than other existing cameras in the market. Not as good as we promise we will, but we hope to get there. Okay, so this is already, we knew it was there. This is already also a real source. This is also a real source image with ALMA. Those three we know that we can detect, and they are in our maps. The complementary maps are a little bit noisier, so we don't see those other fainter galaxies there, but they should be there. And just by running a source detection algorithm, we know that there are other galaxies there. So this is still analysis to come. But this is not what we want to do. What we want to do is to cover large areas and go deep, much deeper than this. So this is what we decided we will go. This is the definition we did in 2018 with the different groups. I mean, it was their Cosmos and it was their candles, and they were all fighting that they wanted the service in their own fields. And in the end, we took the decision that we were going to go for candles, but try to target the JWST, the Cosmos Web area, if our efficiency for mapping is good. So we still hope that we will be able to do that. And in order to understand what we will be able to find, we have been performing mock catalog simulations of what these galaxies will look like to try to test whether our detection algorithms will work well. So this is work by another PhD student, Araceli. This paper is already published. It's a catalog that can be used by anybody in the community. It's not targeted to TolTEC, although our paper actually was exploring how well TolTEC could work for our UDS survey. And there is another paper we're working on now, which is the 100 square degrees. So these are based on dark matter halo simulations. We adopt the dark matter simulations. We construct a cone. We actually piece together, and I will show that here. We piece together a cone that will actually be able to reproduce the area. This is the full area that we will able to see. This is in coordinates, moving coordinates. So for any part of the cone where we have just put together these dark matter halos, evolving them back into the past, we can actually see what type of dark matter halos we have. And now the name of the game, and this is standard for mimicking or for mocking galaxies, is try to associate real galaxies with dark matter halos. So what we do is abundance matching, just knowing what is the galaxy mass function and knowing what is the halo mass function. We associate point to point. So for each halo, we associate one galaxy. And because we have the growth of the dark halo, we know how much mass has grown into that dark matter halo. And we know how much stellar mass has grown into that dark halo. So we have stellar mass at any point in the simulation and star formation rate at any point in the simulation. Then we use some empirical known relationships between how much obscure star formation and how much UV non-obscure star formation there is. This is the measurement of obscure star formation versus total star formation from Whittaker for galaxies which are forming stars up to redshift 2.5. And from galaxies there onwards, we adopted the old star formation history curve of Dunlop, which is actually very pessimistic towards how much dust there might be at high redshifts. It's one of the most pessimistic views of how much obscure star formation we can have at high redshifts. Then we basically associate the obscure star formation to infrared luminosity, and from there to dust temperature. So we have the emissivity at different wavelengths of the galaxy. And finally, we just look for galaxies in the sky around it that could be amplifying. So we do line of sight one by one amplification. Our lensing model is very simple. It's a point-like lensing model. It's not the best, but it is actually time-consuming to actually do all the lines, all the possible line of sights to see how much amplification there is for each of these galaxies. Okay, so this is the observables comparison for the 5.3 square degree type of test. All of these are observational data at 1.1, 1.4, and 2 millimeters. This is the slope measured by the SPT telescope. All here is measure synchrotron dominated galaxies and those that are dust dominated galaxies. We will see that later when we do the 100 square degree survey. This is a comparison for redshifts with ALMA type of surveys, just cutting our mock catalogs to the same observational cuts that the ALMA catalogs have. Tiny areas, so huge cosmic variance, of course, but the redshift distribution in orange, which is the observational one, looks pretty good compared to our mean and to our distributions of cosmic variance over the same type of scales, which are marked here by these error bars. This is how much variation we expect to have just by looking at these tiny fields that ALMA is looking at. Luminosity function is much noisier, so expect to just see a lot of variations, and you see a lot of variations, but roughly it comes among the points. Testing correlation functions to see how clustering is working for these galaxies also looks right on top. And our simulation shows that we should be seeing downsizing. So we should be seeing that fainter submillimeter galaxies, fainter dusty galaxies actually are selected at lower redshifts than very bright galaxies. And then we have the large scale structure, the 60 square degrees. So we had to do the 100 square degree type of simulation. We are here just showing how by taking a larger volume, we actually do good into reproducing. This is the dust-dominated sources from SPT at different wavelengths, and here at 350 microns. So we think that our model is working well for selecting the lensing samples. And then we can do the evolution of rich clusters, which is one of the new products that we have from this simulation. So what we are seeing is a common box in array and deck at different redshifts, from redshift 5.6 to redshift 0.5 of an evolution of a single rich cluster, just showing how at the early stages of the cluster evolution, which will be a protocluster when you select it at redshift 5, you have about 50%, 40 to 60% of the galaxies, all galaxies, 50% are dusty star-forming galaxies. So dusty star-forming galaxies should be a good way to actually look for these protocluster environments. This is what's coming out of our simulations. For instance, if we focus here, we see the full cluster volume just being occupied by dusty star-forming galaxies. ULERCs, or 10 to the 12 solar luminosity type of systems, are in red. LERCs are in yellow. Pristine, not very dusty galaxies are in blue. Okay, I'm going to skip this just to say that, of course, we can reproduce the total star formation history as measured to date. Clusters are not a major contributor. This is where clusters are, but they are an important ingredient in order to know how galaxies evolve in this history of evolution. And we have also the simulations just running through the telescope simulator to try to see how these observables get modified by observations. So the simulations, the mock catalogs are public, the 5.3, the 100 will be public as soon as the paper is accepted. We hope that this happens soon. And this is the summary of results that I would like you to take with you. I will say that much of our knowledge about dusty star-forming galaxies is based on the most extreme systems still. I mean, we do have ALMA and we do have LERC regime type of systems, but we don't have the full census to know how the LERC regime, the 10 to the 11, the more common star-forming dusty galaxies work. This is work we will be able to do with single-dish telescopes and then follow up with ALMA, JWST, and other facilities. So TolTEC comes to that to resolve that question. We have built a cosmologically motivated simulation of dusty star-forming galaxies. The observables up to now coming from ALMA or from the single-dish, more statistically extracted type of samples of bright galaxies are well reconstructed by these mock catalogs, and it gives us an idea of how clusters are formed. So protoclusters are traced by dusty star-forming galaxies at redshifts higher than 1. And we have between 20 to 40% of galaxies that are dusty in these protocluster regimes. I haven't really gone into the boosting and measurements, but of course, because we have a detailed mock catalog with clustering already embedded and with amplification embedded, we can correct much better for systematics like boosting. So how much the faint galaxies are pushing up the flux that we are measuring for bright galaxies, which is a common problem, especially if you have low signal to noise, if you're looking for faint galaxies at low signal to noise. We're just working on TolTEC working. Commissioning is proceeding as we speak. We are still taking data from the field that I have shown you, and we have several small fields, extragalactic, large field extragalactics, large fields, galactic as well, large fields and small fields to look for the polarization and see how well we can reproduce the magnetic fields. But I didn't want to give a comprehensive view on TolTEC because it's not my expertise on research. I just wanted to give you a flavor of what topics I am interested in and how much I'm looking forward to interacting with all of you. And I know we have many common interests and we work on similar fields. I'm hiring, so I will be advertising a postdoc position soon. So if you're finishing your postdoc, or if you know anybody who is interested to come into CAP to work on submillimeter galaxies, please tell them that there will be a position available soon. Thank you for your attention.
Well, thank you very much for that super interesting talk. It's really interesting to hear about these sort of new facilities and how they'll be used going forward. So do we have any questions here in the room? I see some hands immediately going up. Now I have to run around because we're a bit understaffed, but I can do that.
Thank you. It's a very nice talk. I wonder whether you have a strategy already for follow-up of these sources, like getting redshifts specifically.
We are going to rely on the photometric redshifts from the places where we are looking at. If you notice, I mentioned for the UDS, we are going to the candles field. So of course there are redshifts taken there. There are a lot of photometry from optical infrared, and we are going to use the photometric redshifts for most of the galaxies, associating the submillimeter galaxies with the optical infrared counterpart. We will not be able to follow this up with the LMT. They are too faint. I mean, we can access the SPT type of monsters easily. We have published papers on that. We can easily, not easily, with difficulty, but we access Aztec 1, a 10 millijansky source. But certainly we cannot actually access the 0.1 millijansky regime with the LMT at millimeter wavelengths. So we will be actually just focusing on the already established and studied areas of the sky by other facilities. Yeah.
Thank you very much. And next question from Paco there.
Otherwise, I can hear you and I can repeat.
Yeah, it's working now. How much of your research is going to depend on your optimistic and pessimistic view, and how does the GMT compare to the 30-meter or what is planned, like Atlas?
Okay, well, Atlas has an optimistic view. So if you're going to compare optimistic to optimistic, you have to focus on the optimistic there.
Okay.
And Atlas will not do better because it's the same size. It's a 50-meter.
Does the height play a role?
That's so this is the limit. Atlas will not be able to go below the confusion limit. It might have better detectors and therefore extend this confusion limit higher over here.
But the detectors, I think, are the same. So they are kits.
They are kits, but I mean, the camera is not yet built. So between now and when it is built, things will evolve, supposedly. So I will expect it to be very similar at 1.1 millimeter. The advantage of Atlas is they can go shorter wavelength.
Okay, because of the height.
And so then it is complementary. I mean, it's already complementary with Scuba 2 cosmology, with Scuba 2, and Nika has the same type of wavelength, so is complementary, but much more of we put into the plate the same type.
So compared to Nika, I mean to IRAM more or less is.
Well, IRAM is smaller.
Yeah.
And it is at a lower elevation type of site. This is 4,600 meters high.
Already.
So our effective aperture is larger because it's a larger dish, but also because we have much less of the atmosphere just working against us. So the Nika 2 surveys that have been published are over here. These are already measured. Of course, Nika 2 is also already being optimized, so it can actually go deeper. So compared to Nika 2, right now we are doing better, but we are not yet here, not even in the pessimistic line. And that is because a lot of our detectors are not yet connected. When we connected them and we went to the telescope, we discovered that part of our cards of detectors were not well detected, but nevertheless, we didn't want to open the cryostat because that delays commissioning time, etc., etc. So we believe it's going to be very competitive compared to Nika. We don't have any doubt about that. At last, it's a new generation. We will have to see how they perform.
Okay, and when will you know whether it's the optimal or the pessimistic?
So we are hoping to finish commissioning this year. And then based on our mapping speeds for the detectors as we will have a projection of how well we are doing. But our observing strategy is changing as we speak, and we are making the camera better and better. So hopefully this year we will start the legacy surveys. That's our intention. And then we will just advertise what our mapping speed is right now at the telescope with the intention of bringing it as close as possible to the areas that we are showing there.
Okay, thank you very much. Another question here.
Thank you very much. This was a pleasure to see this talk. And I have two short questions. One is wondering about the full width half max of TolTEC. Now that you've actually commissioned it, is it at 5 arcseconds?
It's 5 arcseconds nominally. Right now we are measuring 6, and we're working on improving it.
Yeah, okay. That's not a huge difference.
Yeah, but.
So the second one is a bit more, it's about the faint end of these DSFGs. So what is driving the faintness? Is that they're lacking dust? Could you almost just call them star-forming galaxies then? You're like looking for, or on the other hand, is it just that they are actually, dust fraction is still quite high and they're just smaller?
We don't know. We will have to look and see. Both possibilities are there. Maybe they have less dust, and therefore you will see them more easily at optical near-infrared wavelengths, and they will be a very good correspondence. But we are expecting to have this type of dark SMGs that are being shown in the literature, where you have almost no dust, no emission in JWST type of observations, and then you see this type of bright ALMA counterparts. So I think that there will be a mixed bag. We don't have a preconception. I know we have a preconception because we have a model. Our model is very simplistic. I haven't really gone into detail, but we are implying that we are conforming to the main sequence of star formation. So of course we will have outliers. And how much the outliers play a role? Well, we are up for surprises. Models are just trying to guide us, but I never take models or mock catalogs as the last word of how the universe will work. It's just a guide of how you can make your strategy for doing your surveys.
Okay, thank you very much. Do we have any more questions here in the room? Or possibly a brave Zoom participant who can unmute themselves and ask a question, or type it in the chat and it'll be read out. For now, Ishmael.
Okay, just a quick one. Thank you for the very nice talk. So is there going to be any open time for this?
Yeah,
because
yeah.
I was thinking.
Yeah, sorry. I have been speaking about the legacy surveys because those have been approved. Actually, TolTEC has been advertised within the common observer type of offer of the LMT, but under common risk observations.
Okay.
because we are still delayed with the commissioning this time. I mean, we hope that 2025 will have another open call, but TolTEC might not be offered. But certainly, TolTEC is a common user type of project, and there will be PI proposals that are not related to this. And we hope that there are a lot of PI proposals. We know that there were for this call in 2024. Those proposals cannot yet be done efficiently, which is why we have recommended to wait still to just do them. But yeah, there will be open time. Open time is open for the US, Mexican community and the Spanish community, because there is an agreement with GTC to exchange time. Okay, but the TolTEC team, sorry, the data is going to be public. I didn't highlight it enough. I mean, we are doing these legacy surveys, and they will be open for the whole community to exploit the data. We will have 2 data releases, one after the first year of data intake, the second after the second year of data intake, once the data is scientifically verified. But yes, there will be PI proposals as well.
Okay, then it's excellent time for a pilot study.
Yeah, that's right.
Okay, and final question with Irene there.
Thank you. I have a question about the protocluster results.
Yes.
What was the redshift range, and was that
I mean, I just put the reaches of the clusters we have in the simulation. I mean, this is not the common cluster that we have in the simulation. So because we are building the mock catalog out of a cosmological box at redshift 0 and then evolving it backwards, we find exactly the same cluster at different epochs in different parts of our survey. I mean, this is a limitation of the simulation, but at the same time, is an asset, because then we can see snapshots of what that cluster will look like at different redshifts. So it goes from redshift, here it is, 5.6 to redshift 0.6 at different redshifts. This is where we find it in our simulation. Other clusters, we will find them at different redshifts. And so we have the common statistical analysis of all the clusters in the simulation. And so the extent you are seeing in array and deck, so in angular size, and you have there the scale in comoving coordinates, so that you can basically have an idea of how big the clusters are in physical size in the sky. Okay, thank you. I think that this is a cool figure. I just love it.
Final question, just now.
Just a quick follow-up on this. Do you, because I don't see very well the colors.
Yes.
Do hyperlyrics, for example, are preferentially in the center of this?
No.
Not really.
No.
Okay.
You know, that was our preconception as well. And you can see, so ULERCs are red, and you can see them everywhere. Hyperlurks, there are so few of them. We have very poor statistics on hyperlurks. But you see one over here, for instance. And I think I have a plot on that, which I actually skipped. Well, you can see how few they are. The hyperlurks are here at any redshift. No, there is another plot that we have in the paper, which is where they are located. I'm sorry, I thought that it was here. But no, we don't find them preferentially at the center. So, and the center might not even be a dusty star forming galaxy. I mean, it just happens in the full cluster, but you have to, in the full protocluster, you have to remember it's not a fully formed cluster yet, because we are seeing them through the color. It will be a cluster at redshift 0, but it is not a full cluster when we are studying them. It's just a protocluster.
Okay, fantastic. And it looks like we have a final question from Zoom. So, Antonio, do you want to read it?
Yes, we have a raised hand from Miguel Sanchez. So maybe you can try to mute yourself, so maybe we can hear you.
What do I need to do?
Hello, all Itziar. Just wanted to know, you have started to do deep fields with TolTEC, and from those deep fields you can start getting some parameters of the efficiency of the instrument. How close they are to the anticipated figures?
Yeah, I mentioned that at the beginning. We are doing commissioning still, so we are far away from our optimal values. We are in the way of refining how we observe and how to bring the camera more efficient into our observations. We also are optimizing the surface of the telescope. So part of our inefficiencies right now, we have figured out finally that because for so long we haven't been doing observations at 1.1 millimeter, the dish was not actually as aligned as we hope for 1.1. So we are solving that. So I cannot give you an answer yet. Yes, we are looking into the same fields as we are, but over tiny areas that we will be doing in the legacy surveys. And we can figure out an efficiency, but I am not prepared to give you the number because that number is changing due to the adjustment of the telescope itself.
Okay. Well, that's very important figure to prepare a proposal, of course.
No, of course. We know that's why we are not opening for new proposals yet.
Okay, fantastic. Well, thank you very much again. And yeah, let's say
Thank you.
say thank you.
Thank you again for your time. Bueno.
That one.
Yeah, that's a good level.
Yeah.
Okay, good, because I was worrying about, I know that